So we've got all the roto done now. Now it's time for things to get interesting, because I remember there are two parts to this, right? The roto and figuring out a way to stabilize 3D motion like this. So how are we going to pull this off? Well, if you recall, the traditional method was to camera track and then manually recreate all the geometry. Now, we don't want to manually recreate the geometry, but we still need to do the camera track. So let's start out with that. I'm going to grab the 3D Classic camera tracker because I still rock with that one. And I'm going to set our footage as the source. And I'm going to use our roto as the mask, like that. And I guess we don't need this copy node anymore. Now that we've got this, we will set our mask to be the mask alpha. We will say unknown lens for lens distortion, because we do want to solve for lens distortion. And we know our focal length is an unknown constant. And we want to make sure we have a lot of points. By default, the number of features is 150. I'll go to the settings tab, change this to like 1,000. So since I increased that by a factor of 6, I'm going to decrease the feature separation by a factor of 6, down to 2. I'm going to preview the features to see where they'll go. We probably want to erode our alpha a little bit so they stay away from the edges a bit more. Like that. That's good. And we do want to make sure, maybe lower the detection threshold a little bit so we can get some more features in there. That's looking good. And we want to check refine feature locations. Cool. Now let's let it cook. Okay, so we've got our points tracked now, and from here we can do a solve. So I'm going to go ahead and hit the solve button in the camera tracker menu, and it's going to do its thing quick. And there we go. So it's solved the locations of many of the points, and it has not figured it out for some of the other ones. And so now we can work on refining our solve. So I'm going to go over to the auto tracks tab. You can see our solve error here is 1.6 or so. Ideally, we'd like to get it around 1 or under 1 ideally. So I'm just going to go here. Well, we've got a bunch of them that are already unsolved or rejected. So we'll just go ahead and delete those. And following that, we can just sort of iterate on this. We're going to refine the solve, make sure focal length, position, and rotation are checked. Hit that. That should make a small difference at first. But then we can go in, adjust the minimum length. We want tracks that are sticking around for a while. Delete any that are rejected. Refine the solve. A little better. Now we're going to bring down the max error, bring down the max track error. Go ahead and delete the rejected and refine. And we repeat this until we find the maximum number, until we find the maximum number of points that we can keep where we still get a good solve. And we're really approaching that now. Delete that. Oops. There we go. Solve error of 1. Not bad at all. We can work with this. Now we got to think. We've got our camera track, and the other piece of the puzzle, or the traditional method, is to have scene geometry. So let's try and figure out a way of recreating this without putting in any manual effort. We'll go over to the camera tracker tab, see what we have for options for exporting. Well, okay, we've got a point cloud, we have undistortion, we have camera. It looks like the point cloud is going to be our most useful option here, so we'll create that. I also do want to create an undistortion and a camera. We'll use those later. And now here, let's take a look. This is our point cloud. And you can see it roughly resembles our scene. And you'll notice that since we masked out our subject during the tracking process, there are no points that are locked onto her. So this is just describing the 3D shape of the background. But you'll also notice that it's sparse. There's nothing in between these points. So if you can imagine, if you can remember the demo that we did earlier, we couldn't really project video onto this and then play it back. Or could we? Let me show you a cool trick. So if we set up a quick scanline render here, like this. We'll plug in the camera, we'll plug in our point cloud, and then if we take a look at the render, you can see there are the points. And just before I go any further here, if you chuck down a reformat and set this to like a quarter scale, and plug that into the background of the scanline render, that'll just make it render at a lower resolution, and it'll make the next processing steps we have to do a little bit faster. So I've done that, and then I'll turn down the point size so that it matches its original scale. Now what? Well, a lot of empty space in between these points, right? But now we're working in 2D space, and so we have a lot more options for what to do with nodes as opposed to working in the 3D toolset. So let's use an in-paint node. Okay, we can plug that into our scanline render and set the fill region to source inverted alpha. Now, this is cool, but you look at this, like, what are we going to use this for, right? Well, we're not interested in the RGB data. We're interested in the depth data. Because if we in-paint the depth data, like this, now we have a pair of a complete depth image, densified depth image, and a camera. And with that pair, we can work out where every point on this screen is by using a depth to points node. I'll save now. Camera, image, and we can take a look. I will make sure this is actually inpainting everything so that we can see something in the 3D space. And now look at this. Now we have, it almost looks like a mesh, right? We've got this whole scene represented in a more dense way, but there are still holes, and there's still the issue that we can't really project. Well, we can kind of project onto this, but look. So what we could do here is put in a copy node, copy our Shift X to swap inputs. There we go. Copy our depth from the in-paint onto the image data from the image. Oh, and we are going to need to make sure that it's the same format, like so. And now we've sort of got our image projected onto those original points. But if we were to render this for our camera, you can see that there are a lot of holes. And the quality is not so great because the points are large. So if we try to decrease the point size, get better resolution, okay, this is looking nicer, but now we got more holes, so we increase the point detail, and now the render really starts to slow down. The more we increase the point detail, the longer this is going to take. And we're always going to have holes. And it's still not even fully high resolution. And not only does it not quite look very good from the direct head-on projection angle, but if we were to look at this through a frozen camera, like so, which would stabilize it, we get even worse artifacts like this over here. So how can we remedy this? This is where ST maps come in. ST maps are so cool. If you haven't heard of them, now's the time. My favorite way to get one is just to bring up this thing. you saw what I typed there, and then just steal this expression node and then delete everything. Although, if you want to just memorize the expression, it's x divided by root.width, y divided by root.height. That is, the red channel is goes from 0 to 1, depending on how far right you are, and the green channel goes from 0 to 1 depending on how high up you are on the screen. So it's a coordinate system, and this allows us to map a transformation to any image. So if we have a transform like this, we can do anything we want to this ST map, skew it, put it in the corner, whatever. And then if we use our CST map node, we can plug this in as our map, set the map channel to RGB, red and green, and then set the source to our image, and it will get mapped to that ST map. Now keep in mind, this STMap node doesn't know anything about the transform node here. It just sees this set of pixels as an input. And another nice thing about STMaps is that they are a continuous field. There's not any details that are present in the STMap that is necessary for the presence of the details in the mapped image. And what I mean by that is if I were to blur this STMap, what you might think would happen is that the resulting image gets blurred. But it doesn't. The outside edge gets warped, but the inside stays intact. And we can take advantage of this because, follow me on this. We take the STMap, we plug it in instead of our plate denoised image. And now what we're rendering down here, I shouldn't have deleted that, object, camera, we're rendering the STMap. And if you remember, we're allowed to blur the STMap and it won't compromise the quality of the final image. So we can render way less points, like this many, bring up the scale, well, maybe a little bit more, this many. Now we can blur it, like so, unpremultiply it, and we've got a completed STMap. And you'll see there's still some issues here. We can just increase the blur a little more to take care of that. And what do we got now? If we plug in our STMap to here, well, there it is. And the cool thing about STMaps as well is that with the C STMap node, you can run them either in forward or inverse mode. So the forward mode is going to sort of double the existing motion of the camera, which looks crazy. And that's also not properly working because we're currently generating a new point cloud every frame. We do want to just keep the one point cloud. So I'll put a frame hold after the depth of points. Put that there. And so now it's sort of doubling the motion that's in the frame. That's not what we want. But if we run it in reverse, inverse, check this out. It's all locked down. There's a bit of weirdness happening over here, but the background isn't moving. It's all locked down. And remember, we didn't have to do anything to do, like, you know, lining up the box or whatever, like, you know, going back here and making 100,000 little cubes for all of these pieces of wood and everything. No, it's all taken care of automatically. And there's some artifacts here. We can take care of that if we check interpolate. That's taken care of. There's some weird sort of waviness happening. Just increase the blur. We're all good. And look at how stable that is. Of course, the warping gets really bad by the end of the sequence, but if we simply set our frame hold to the last frame, then it looks normal on this frame. Well, relatively normal. And it gets weirder the further back we go. If we set a frame in the middle, this is going to be our reference frame. Sometimes it gets a little buggy here. You just have to sort of, you can delete the cache, and that does nothing. That's not even doing anything. Okay, sometimes the frame hold will get stuck like this. Like currently it's referencing frame, the last frame, 65, even though we have it frame held at 35. So there we go. Just gotta let it load. I'm in the 3D space. Maybe switching to that helps. And then we can frame hold on frame 36, and then it'll stick. Anyways, got this now. Look, we can set our reference frame wherever we want, and it keeps it stable. It keeps it locked off. And the best part is about STMaps is that they are reversible. So we can put another CSTMap node down here, plug our map in again, and put the source as our already distorted image. And then instead of setting this to inverse, we set it to normal forward mode. And all of a sudden, our original image is recreated. Granted, there's a bit of artifacting happening here, but we're keeping the area around our character untouched. And so now we can modify the image in between these two things, and it will stick with the movement of the background. So I could go in here with a grade and put down a roto node and grade this patch over here to be, you know, brighter, and it doesn't exactly stick to the exact spot we wanted. But now that I've just done that, I don't have to animate that mask at all, and it'll stick with the background. Isn't that cool? And so now you see how this can be a pretty cool technique. All right. And so let's figure out how we can use this to do an in-paint. So if we look back at this third demo that we did, the stabilization one, we can see what our workflow is one more time, just to remind ourselves. We start with the original plate, we stabilize it, we do our time echo thing to it, and then we reapply the motion. Stabilize, then reapply. And if we look back at the file that we've just made, we're doing the same thing. We have plate, stabilize, and then reapply the motion. So all that's missing now is the time echo step. So let's try it. All we got to do is bring in our roto, and we want to use the lens distortion corrected version of our plate, so we'll plug that in. And actually, did you just notice that there is a bump in height when we apply the lens distortion? If we look at the lens distortion node itself, it's not doing that. What gives? Well, that's an ST map thing. Something to be aware of is that ST maps are very sensitive to bounding box changes. The bounding box of the footage that it is receiving and the bounding box of the ST map need to be the same. So the ST map was 2048 by 1080, and the lens distortion version, you can see it changed the B box to be 2045 by 1083. So that's not going to work. And all we need to do is put a crop after this, turn off black outside because that puts a little border around it. Now it's matching 2048 by 1080, 2048 by 1080. And if we look at the difference, crop off, crop on, big difference. And it could be a lot bigger of a difference too. So anyways, back to where we were. We're putting the roto down this pipe to our ST map. I'll hit K to bring up a copy node and put our alpha in. And now we've got it down here. We need it to be inverted, so I'm going to do that up here. Do an invert on the alpha, and I'll put the pre-mult on so we can see what's happening. Looks like there is a little bit of an issue with the edge coming through, the hair is coming through, we don't want that. So I'll grade. Anytime you're grading alpha, turn on white clamp, and we'll bring the black point up. And also make sure that we're grading the alpha, not the RGB. Bring that up. And that's looking good, and we want to erode it a little bit with a fast erode. And look at that, it's messing with the bounding box again, and it's doing weird things. Put a crop after, don't black outside. And now we're good. Just trying to include as little of the hair as possible. Cool. So now let's take a look at what the time echo does. Let's try it. Time echo. We'll say time echo. Take me to the last frame. Look at the last 65 frames and give me the average, please. What do we get? Okay, well, we get the same thing that we got in the other thing. We still need to unpre-multiply. Let's do that. Unpre-multiply. And this is actually quite good. Look, let's look at the motion re-added version. And you can see, oops, nope, we still need to frame hold it. Like that. And now we can see this looks pretty darn good. It's almost exactly what we're looking for. There is our clean plate, sort of, and our original plate. We're getting there, but there are a lot of artifacts. So let's take a look at how to clean up these artifacts. Okay, so right off the bat, one of the largest artifacts, or one of the most noticeable artifacts that I'm seeing here is this sort of wiggling that's happening at the edge of the frame. And this is happening because we have points in our ST map render here that are leaving the edge of the frame. And as soon as they leave the edge of the frame, they're no longer contributing to the reconstructed map. So to remedy this, what we can do is actually just render in the scanline render on the scanline render tab, there's a little overscan. And this will grow the bounding box of our render a little bit more, so it's rendering outside of the frame. And this will give us a little wiggle room here. Let's see if 50 pixels will work. And of course, we are going to have to crop our ST map to make it work for the CST map node. And look at that. The flickering, or the little bumping on the edge, is pretty much fixed. Next up, there's this big sort of black haze over here that I'm seeing. What is causing this? Well, let's just scrub through our pre-time echo pass here and see what's going on. There seems to be, well, a big black bar that's coming through here. And if you notice that, the alpha does not account for it. We've got a big hole here, but it's counted for because there's a hole in the alpha, which gets negated by this unpremult down here, but we're not getting it up here. So where's this black bar coming from? It's coming from up top, where we have a lens distortion that is introducing a tiny little thing at the edge of the frame. And it's not in the alpha channel because we're overwriting the alpha channel with this copy node. So all we got to do here is just shuffle in an alpha channel before our lens distortion, because actually right now there is no alpha channel. And then make sure that we are clicking this little half circle here to white it out. And now we have our little edge here accounted for in the alpha, but we're still overwriting it with this copy node. So I'm going to go ahead and drop down a merge node, turn off the red, green, and blue channels, so we're just affecting the alpha, and then go ahead and set this to multiply. What we've got now is a merge between the two alpha channels. We have the hole here and the hole here. Let's see. It didn't fix it fully, but before, after, that did help, but there's still something here. What's causing that? Let's take a look. And I believe it is actually because of all of this extension that we have going on here. This is my mistake. I turned on interpolate earlier in this ST map to try and clean up the edges a little bit, but it wasn't really helping. So I'm going to disable that. Now we have this. Check again, and that helped a lot. This is before, after, much cleaner. Although we did get a new artifact, which is these sort of striations at the top of the screen, horizontal lines. And this is caused by the sharp edge at the top of the screen. We don't want this. So what we can do is soften this edge by using a crop node. I'm just going to, before the lens distortion, crop. We're going to use a soft crop. The softness here will bring in an edge like that. But we also just want it to apply to the alpha because remember, we're doing our pre-multiplication down here. We don't want to do a double pre-multiplication. So I'm going to use a copy node, just copy the alpha from the crop, leave the rest of the image alone. And let's see if that helped. Yeah, this is before, this is after. You can see there is a bit of a line here that got cleaned up. Okay, well, what else can we do? What other artifacts do we have? Well, there is a big hole down here. This is an example of a part that was not revealed during the duration of our original clip. You can see that little bit down there never gets revealed. And so it is an empty hole in the final version. And in order to fix this, I'm just going to use an in-paint node set to source inverted alpha. And that'll fill it in. We've pretty much got our background plate all in-painted now. Look at all this detail that we've gotten from behind the person. And it looks pretty good. But obviously, there's some areas like over here that don't look so good in this version. Luckily, we do have them in our original plate. They're not being obstructed by our character at any time. So let's try and merge our original plate with the in-painted area. And it's always a good idea to try and do this anyway. It's the principle of VFX is you touch the plate as little as possible. So we're going to try and use just the area that we need to cover up our subject from our in-paint. We're going to go ahead and just grab our alpha channel from up here where we did all this work on it to make sure it encompasses the entire character and copy that to our output in-paint. And we've got that in there now. It's inverted, so we do want to invert it again. And now, oops, just the alpha channel. Now we can pre-multiply it. And we've got a patch that covers just the area of our subject. Let's go ahead and merge this over the top of our original plate. Put this over here for organization purposes. What are we looking like now, huh? Let's take a look. Well, it looks pretty good, but it's a little bit obvious that something has happened here, right? You can kind of tell. So what can we do to remedy this? Well, first things first, let's see if we can, well, there's some hairs visible here. Let's see if we can feather out the matte a little bit. For this one, I am going to use the filter erode because it lets us do a sort of blurry dilation. Set the method to Gaussian and expand it like so. Okay, that's looking better. Not as obvious anymore. However, you can still sort of tell that this area is a different color than the rest of the image. And that's because throughout the duration of the shot, if you pay close attention, the brightness does subtly change the exposure. Or there's like, you know, glare hitting the lens, and it slightly changes the color of the image from the average color. What we have here is the average color. So how can we match this? Well, we could go in by hand and say, okay, this looks too dark. I'll bring up the gain on this grade. There, that looks good. And then now over here, it looks still too dark, so I'll bring up the gain more. But now it looks too dark on the top and too bright on the bottom. Maybe I can use a mask. Let's get Nuke to do this for us. How about that? Now, this is one of the coolest techniques I know how to do in Nuke, so pay attention because I use this like all the time. This is automatic color matching. So how do we do it? Well, here's the principle. We did like a manual version where we're adjusting a multiplication for matching the brightness between the patch and the background plate. So what if we had an image that we could multiply by instead of a single value that would perfectly describe how much brighter, how much darker the image needed to be in order to match perfectly with the background? Well, let's make that. So we need an in-paint node, and we need an identical in-paint node. I hit Alt-K there to clone it, and what I'm going to do is set the fill region to matte alpha, and we're going to set the matte to the alpha matte of our patch. And we're also, for this in-paint here, we're going to set the source to be this very same node. But for this other one, we'll set the matte to be the patch alpha again, but this time we'll set the source to our plate, our background plate. So now we've got these two, and let's take a look at what they're doing. The idea with these in-paints is, if we've got a patch, we will have something removed from, or something that's different from the original background plate. So in order to do a proper comparison between the two, we need to make those areas the same. We do that with an in-paint. This will in-paint the area where our different area is. So now we have two different images, our original background here and our patch plate, with the areas that are supposed to be different, both in-painted in the exact same way. And what this lets us do is compare the rest of the image. And we can see there is a difference in brightness, like especially over here. And so let's do the comparison. We do this with a merge node under the divide operation, and we'll hook this up, B, A. We get an image like this now. If we were to multiply this B input by this divided output here, multiply, what we would get is exactly the A input of the divide. You can see this is the same as this. And this isn't that useful, but when it really starts to get useful is when we add a blur after the divide. Because you can see there's all kinds of little details in here, making it so that the multiplication will exactly match this A input here. But if we start to blur, what happens is that we only keep the low frequency changes in the image. You can see this isn't getting blurry because I'm blurring. This is getting blurry because the A or the B input here to our divide is blurry already. What it's doing now, if we turn off and on the multiply, is just doing a brightness adjustment to match it perfectly to the A input of the divide. You can see now, low frequency matches perfectly and the details are different. And so now, Beauty is we can apply this to our patch over here, send it on its way down to the pre-malt, and now let's see the difference. Turning this off, this is our before. There's a line here. You can see where the brightness didn't quite match up. And now if I turn on this multiply, turn off the alpha. If I turn on the multiply, now it matches perfectly. And it does it for every frame automatically. So on any given frame, it's going to match perfectly. And we don't have to do anything by hand. No manual grading, no masks or anything. I love this technique. Although, in its current form here, you're going to notice some flickering happening. And what can we do to solve this or to remedy it? And the main thing we can do is try to increase the smoothness here on our in-paint. This will increase the temporal consistency. As we get more of that, it starts to get a lot better, for sure. We do get still some of that issue. And really, the reason of what's causing it is that there are details present in our original plate that are not present in the patch. So when it's right on the border of that in-paint, and it's visible in one but not the other, for example, the edge of this stick here, there it's visible, there it's not. There's a large difference between these two colors, and especially on the next frame, the previous frame where it gets completely wiped out, then it's very much more similar. So that's what's causing the flicker. And turning up the smoothness helps a lot. We can also do a time echo again, like this, time echo. We'll do an average over a few frames, and this will certainly help things out. Now, this is pretty good. This is a pretty good result. And depending on your project, this may be acceptable, but it is pretty smeared here. And we've been using all stock nuke nodes up to this point, but there is a node that can help us out with this issue. So I'm going to be using a node called PXF Time Merge. Now this is a lot like Time Echo, and there will be a link for this node in the description. It just has more options for operations that we can do. Instead of just average, max, and plus, we have many more. So in addition to that, we also have controls like frame skip, which lets us do, every other frame or every 3 frames or 4 frames or whatever. Let's do exactly what we did with the time echo. Frame 65, we say we want to go backwards this way, and we want to use the over operation. What's this going to look like? Well, let's go one at a time here, adding more frames. And we'll do a frame skip of 2. And we can see it's starting to fill in the detail as it would with time echo. However, all of our wood pile stuff is staying sharp. See, if we compare the difference between this and time echo, we can see that we retain so much more detail in these sticks and planks that are on the right side here. They were completely smeared out before in our time merge version. However, in exchange, we do get some other artifacts. For example, we have this sort of darkening of the area over here. We have this hard line in the middle. So how can we fix this? Well, here's what we do. Let's do an erode. We will use a filter erode again. We'll do this before the pre-malt, like that. And now you can see that hard line in the middle just going away. But we still have the issue of this dark area. Now, why is this happening? Well, as I mentioned before, the brightness of the shot changes throughout the duration of the shot. And we can see that happening here. There's a vignette on the lens, and it's affecting the brightness as the camera moves. So what can we do? Well, it is simple. We'll use the same color matching technique that we used down here, up here. So I'm going to copy these nodes that we already set up, paste them up here. I'm going to use Shift-Alt-K to declone this paint so it's no longer tied to the ones down here. And then we'll clone it again to make a matched pair like this. So we need a reference frame and we need our current frame. So let's set that up. Our reference frame, we're going to pick a frame that's sort of in the middle because it's not going to be too different from the frame at the very beginning or the very end. So we'll do 35. And I will drop down a frame hold node, hook that up here. Actually, I'll do it before the pre-mul. And then I'm going to go ahead and hook up our source, and we're going to want to invert our alpha like this. Great, now we've got that inpainted. Same thing for over here. Oh, we got to make sure this is hooked up to the regular source, not the frame held source. We need to make sure that our two inpaint nodes are not wildly different from each other. And here we see we've got the character in one and not in the other. So we're going to need to do a composite matte between the held frame, which is this, and the current frame, which is this. So we can see what this looks like. Oops, we will use the over mode, just the alpha channel. And we can see, oh, we want to put this invert before the frame hold, like that. And now, yep, there we go. So now we've got a combination of these two mattes, the current frame matte as well as the frame held matte. We put these together, make sure that they're both hooked up to the same matte source, this one. So now the only non-inpainted areas are areas that are supposed to be the same, like that. So now that we've got this image that describes the change in brightness that we need to have to stabilize it over the course of our shot, we apply this to our input to our time merge, like this, with the multiply. Of course, we will need to do a blur to make sure that the details don't come through, just the low frequency changes. And we can see what the result is. Oh, we will have a problem unless we uncheck the alpha. So this is already much better. We can see without the brightness correction in here, we had this, and now with it, we have a much more equal looking image. And of course, we'll do our unpremult at the end, clean everything up. So yeah, just like with our time echo, we still have holes where there was no data. So we'll plug this into the same in-paint setup and frame hold that we had before, like so. And now you can see exactly how much sharper all of these things are. Let's take a look at our final result again. Bask in its glory. Oh, and one thing you will notice here, there is a bit of a divide here. Remember, before we feathered out our incoming matte, there was a hard line right here. And you can see that it still sort of exists, it's just feathered. And the reason this is happening, despite our brightness correction, is that we have not decreased the smoothness back down. I'll turn that all the way down, and you see that will clear right up. Now we do have an issue over here. It's a bit like whack-a-mole with this, but we get there eventually. There is a bright blue spot, and this is happening because we're getting a blue color in our divided image, like this. And to fix this, this happens when we have a very low value in one of our sources, so we can just pop a little grade in here, clone it with Alt-K, put it on the other input, and then we just put a tiny little bit of lift in. Try 0.01. There we go, fixed. And just to be safe, we will do the same thing down here on our other color correction. That happens, you know what to do. And the difference is definitely pretty big. We have a much cleaner looking result, in my opinion. The stick here really lines up a lot better. Let me play the other version that we had before with the time echo. And our version with PXF time merge, much cleaner. So of course there are still a few nitpicky details that we could pull out, like this line, even though we did help it by decreasing the smoothness amount in this in-paint, it still exists. And this is, we can mess around with different frame hold values, like if we set this closer to the beginning of the comp, that actually improves it quite a bit. That is one way to help it. There's also the issue of this trailer not quite sticking. This is a bit of a problem. And there are a couple different ways to solve this. It shows up because of an inaccuracy in our depth pass to begin with. There's not enough data on this edge. So what we could do is actually go into our point cloud render, this one, and you can see how sparse it is here. We could actually line up manually a plane with our footage. And you could do that using Model Builder or something. And just real quick, I'll show you what that looks like. Now we've got a card at roughly the right depth, and we can just go ahead and export this, bake the selected geometry, and merge this into our little scene like this. Put that in there. And now that's going to come through in our depth pass like everything else. And it should help us get a bit more of an accurate solve on that trailer. Let's take a look. Yep, now the trailer is pretty much rock solid. Have a look at that. No problems. Look at our final version here. And yep, a lot more solid. We still are getting not quite a full match here, and it might be because of this grade. Yeah, it's because of the grade. Too much strength on the grade. We just need a little bit of lift. Going down to like a 1/10 of what it was before. Oh, and one more thing. It will not line up exactly perfectly properly unless we redo the lens distortion after we do all these steps down here. So I'll put it right before our pre-mult here. And I'll set it to redistort. And that will just ever so slightly nudge it back into place. So here it is. This is our final result. And I think it's pretty amazing that we did all of this with a node graph that is just this big, especially for having to do pretty much no manual reconstruction of the geometry, with a small exception for this trailer here. But you can see how powerful the techniques involved in today's video were. And I really hope you picked up some ideas for ways to use this in your own workflow. Once again, if you want to follow along with this tutorial, all the resources you need are in the description below. We have the footage, we have the nuke scripts, and we have the gizmos, all linked. Go and grab them, go and try it out, it'll be cool. I'd like to thank the Foundry for having me here on their channel, and I'd like to thank you very much for watching. My name is Julian Cruiser. You can find me at nodesaren'tscary.com or here on YouTube at nodesaren'tscary, and I'll see you around.